and welcome to the fifth lecture of this course. In the last week, we started with the concept of sampling distributions and we focused on single sample problems, which means that we basically considered a normal population and from there we drew a sample, and there we studied about the sample mean, sample variance and sample proportion. Now, there might be situations where you have two different populations or they are coming from the same normal population with different means and variances, and then you want to compare the sampling distribution of the sample means. Okay? So basically you are interested to find out the sampling distribution of difference of sample means. In that case, we will see what are the different cases we have. Similarly, you might be interested in sampling distribution of ratio of sample variances. And lastly, you will also see the sampling distribution of difference of sample proportions. So we are going to dissect this topic and complete this concept of sampling distributions with today's lecture. So let us begin with the first one, that is the sampling distribution of difference of sample means. In this case, first of all, if you assume that the two samples are independently drawn from the population, then what are the different scenarios where we can be interested? See, if you are considering that they are coming from the normal population, then there will be two parameters for the first population and similarly there will be another one for the second one. So you will have mu1 sigma 1 square and mu2 sigma 2 square. Now since your interest is in mu1 and mu2, or rather mu1 minus mu2, so what is left is the other parameters. Now there are certain conditions based upon which you can identify the sampling distribution. Now the first situation can be that the two variances are unequal but they are known to you. Then what will be the sampling distribution of the sample differences of the sample mean? Next can be that they are unequal but they are unknown to you. Okay. Likewise, they can be equal, all three can be same, that is the two population variances are same as sigma square and they are known to you. And lastly, you can have them same but it is unknown. So we all know that unknown situation over here is a more practical scenario. Okay, like this, and like B and D are the more practical situations which we encounter. So we will see each of them, and also when we have dependent samples, then how do we deal with it? So we will begin with the first one, that is the two independent samples. We have sampling distribution of difference of sample means. In this case, the first theorem over here, if you see on the heading that I have written, that the two variances are unequal but they are known to you. And if you recall from the previous lecture, whenever sigma square is known, then the sampling distribution of the sample mean followed normal distribution with the same mean, but the variance gets divided by n, that is the sample size. So now let us see how that result gets transformed when we are focusing on two sample problems. So the result says that if you are drawing independent samples of size n1 and n2 from two populations, whether it is discrete or continuous, and the means for them are mu1 and mu2, variances are sigma 1 square and sigma 2 square, then the difference of their sample means is going to follow normal distribution with this new mean and this variance. Okay, so let us see the proof for this first. So let us begin with the first theorem. Here what we are given is that the two samples, the first one is of size n1 and the other one is of size n2, and they are coming from a population. Okay. So we know that if they are coming from normal population, then obviously if you have the sample mean, that is x1 bar, then this will again follow normal with mean mu1, and variance will be sigma 1 square by n1. Right, this we have already seen. And also if you consider the second one, then that also would be following normal with mu2 and variance sigma 2 square by n2. So if it is normal, then it is definitely going to be this. And we also have seen the central limit theorem that even if you are not taking it from a normal population, but if your random sample that you have taken is of the size is large, then it is going to be basically following your normal distribution again. So ultimately, in both the cases, your sample means would be normally distributed with these parameters. Now, we have to find the sampling distribution of x1 bar minus x2 bar. We have to find this distribution. The point is, if you notice over here, we are interested in x1 bar minus x2 bar where both are normally distributed. For this, we have a result which says that if you have independent and normally distributed random variables, then their linear combination would still be normally distributed with a certain mean and variance. So, if you have different xi's coming from normal distribution with mean, mu and variance sigma square mu I and sigma I square, then y, if you define, which is the linear combination of these, I is going from 1 to n, and y is again going to follow your normal distribution, and the mean would be summation ci mu I, and variance would be summation ci square sigma I square. Okay. So if these xi's are independent, then their linear combination again would be normally distributed, and this could be very easily proved through the MGF technique, because if you take this moment generating functions, so we know that if I have to find the distribution of this new random variable y, then I can very well use the MGF technique over here, because we know the MGF of the normal distribution, right, which is e raised to the power mu t plus sigma square t square by 2. Okay, so here my moment generating function of y at t would be nothing but expected value of e raised to the power ty, and what is this? E t, and y would be summation ci xi's. I is going from 1 to n. Right? Now if you expand this, what you will get is here e power t times c1 x1. Okay, so here this will be plus t times c2 x2 and so on up till cn xn. So if you look at that separately, it is moment generating function of x1 at tc1. Likewise, it will be the moment generating function of x2 at tc2, and likewise it will go up till the last one, because they are independent. Okay. Now what is the moment generating function of x1? So basically all of these would be here. It will be the product of I1 to n, because all these xi's are coming from normal with mean mu I and sigma I squared. So given this MGF over here, we can very well write it e to the power mu I t. Since instead of t we now have c also, right? So ci t plus sigma I square by 2. The formula is sigma square t square by 2. So instead of t you have CIT, so CI square, TI square. Okay. So this you can also write it as T summation mu I CI plus, so if you want the TI square, it would be just T square. So there is no I over here. So this one would be t square by 2 summation ci square sigma I square. Right? Now if you compare it with the MGF, so here I is going from 1 to n, and here also I is going from 1 to n. So if you compare it with the MGF of the normal distribution, you would see that it follows normal with this mean and this as the variance, because that is the difference here, and MGF is unique. So let us write it. So it will be summation ci mu I and summation ci square sigma I square. So this is the result we know very well. Now, if you will apply the same thing, what you are given in this theorem is x1 bar minus x2 bar. So here you only have two terms which are normally distributed, and if you consider their linear combination, so here basically C1 is 1 and C2 is minus 1, which means that this x1 bar minus x2 bar is going to follow normal with mean is C1, right? So it will be summation Ci mu I. So first one will be mu1 minus mu2, okay, because C2 is minus 1, and here the other one would be here because it is sigma 1 square by n1. So this one would be sigma 1 square by n1 plus sigma 2 square by n2. Okay, because Ci square, C1 square would be the same. So here that will also be 1 plus 1. Okay, so sigma 1 square by n1 plus sigma 2 square by n2. And we know that if we standardize it, then obviously it would follow, we have seen in the last lecture also, this would be following your standard normal distribution. So minus mu1 minus mu2, this again, if you bring this down, sigma 1 square over n1 plus sigma 2 square over n2, this one would follow normal distribution. So this is the result that we have now just seen the proof of this. So you can see that this is very easy to prove also, because in this case you know that the two variances are known to you. Okay, and this result holds even for the distributions which are not normally distributed, because the central limit theorem would still be playing a role over here, and we can still say that the x1 bar follows normal. Again, the sample means follow your normal distribution with their respective means and variances. So now let us see an example for this. So during a competitive exam, a reasoning test is administered over 2-day period, specifically on Monday and Tuesday. And on each of these days, 10,000 individuals participated in that examination. Now, you know that the scores for the Monday test follow a normal distribution with the mean as 68 and standard deviation as 8. Similarly, the scores for Tuesday also follow your normal distribution with mean and standard deviation as follows, 52 and 9. So, given this information, you need to find out that if you randomly choose 25 individuals from the group who gave the exam on Monday, and you denote their average score as x, in the suffix you write m in order to denote it, that is a sample mean for the Monday, and similarly you select 20 individuals from the group who took the Tuesday exam and you denote it by the suffix you add over here as t, then what is the sampling distribution of this difference? Okay. Also, you need to find out that what will be the probability that the difference in these two means, the average scores, is 10. So it basically means that the difference of the two sample means is greater than 10. So let us see how to solve this. So in this example, we have the sample mean for Monday is following normal distribution with the means that was given to us as 68 and standard deviation was 8, which basically means that sigma square by n. Okay, and 25 individuals were taken. So basically it would be 64 by 25. Okay. Likewise, for the second day, it is again following normal distribution. So mean was given to you in that case as 52, and your variance again. So standard deviation was given as 9. So it means square of that, since sigma is 9 in that case, and n2 was 20. So sigma square by n2, right? So it would be 81 by 20. Now, with this information, you can simply just apply this result and say that normal would be mu1 minus mu2. So this is mu1 in this case, and here this is mu2. So this will be 68 minus 52 and 60 sigma 1 square by n1 plus sigma 2 square by n2. So you can solve these and you will find the sampling distribution of the difference of these sample means. Now if you have to further find out the probability that this difference in these is greater than or equal to 10, we know that we can standardize it, right? So here it will be same as probability. So xm bar minus the other one. You subtract the two means, right? That is 68 minus 52. So 68 minus 52. And you have this as your standard error coming here. So I'm just writing it. So here also 10 minus of 68 minus 52 divided by the standard error that you have. So let us say that the standard error is basically the standard deviation of the sampling distribution. So this is basically your variance actually. So this would standard error would be the square root of your this variance term. Okay. So this over here, this is basically your z. Okay, standard normal variate, and if you simplify this, so it would come out as negative and some value around 2.33, right? And you can look at the standard normal table and it comes out approximately 0.91. Okay. So in this way you can solve the problems, and note that we are not always interested directly in the sampling distribution of this, but rather our interest is in finding out such probabilities. And you cannot solve these probabilities until you know what is the sampling distribution of this, because then only you can apply your standard normal distribution and the concept of standardizing it, and the result will follow. Okay. Now we come to our next theorem, where although we assume that it is known to us, but here what we see is that they are same. Sigma 1 square, sigma 2 square is same as sigma square. Okay. So in this case, so we are basically, so A, B, C, D, I think initially I said that B is the unknown one. So let me just go back and see. Yeah, so here I wrote that they are unknown. So rather I am first tackling with the C over here. Okay, so I am first dealing with the known cases and then we will come to the unknown ones. Okay, so do not get confused with these numberings. So here, when it is known, then obviously we know that again, it is very simple from the previous one and we follow from that, because if you are taking out two independent samples of these sizes from two populations with their means mu1 and mu2, and now they have a common variance sigma square. Unlike in the previous one, you had two different variances. Okay. In this case, same again from the same concept, same steps will be there. It will again follow normal distribution. Mean would be mu1 minus mu2, and here you can take out sigma square outside because it is common in both of them, right? And when you standardize it, you will get this. So sigma will be this and under root 1 over n1 plus 1 over n2, and it will follow normal 0, 1. It is very easy to see because in the same one you would have x1 bar following normal with mean mu1 and variance sigma square by n1. Likewise, x2 bar would again be following normal with mean, mu2 and variance sigma square by n2. So when you take the difference of their sample means, by using the same logic, that the linear combination again would be normally distributed with mean summation ci mu I. So that is what mu1 minus mu2. Their c1 is 1 and c2 is minus 1, and likewise for this one. Okay. Two separate experiments. The battery life of two different brands of smartphones is compared. In the first experiment, 20 smartphones from brand A undergo testing and the duration of their battery life is recorded. Similarly, you do for the second experiment, that is 25 smartphones from brand B are also tested and their battery life is likewise found out to be normally distributed. So you know that both are coming from the normal population. That is why even 20 and 25 is working with this case. Otherwise, you should have taken more sample sizes of size greater than 30. It is known that brand A smartphones have an average battery lifetime of 17 hours. That is, mu A is given to you and mu B is 15 hours. And their population standard deviation for both the brands is 2 hours. So that means sigma 1 square is same as sigma 2 square, which is same as 2. Okay. So everything is given to you and you just have to substitute the values and you would get the answer using this secant theorem. And you are essentially asked to find out the probability that this difference is greater than or equal to 0. Okay, so which basically means you are finding out the probability that the sample mean or the average lifetime of the smartphones coming from brand A is more than that coming from brand B. Okay, so let us see how we can solve this. So let me just note down what is given to us. So this is your second example. So x a bar follows normal. So mean over here is 17 and variance is 2. And the unit number of this is Since your standard deviation is given to you, it means that variance would be 4. Right? Similarly, xb would again be normally distributed with mean. Mean over here is 15 and variance again would be 4 by 25. This is what is given to us. Okay? xa bar, it is normally distributed. Okay, so mean, and this is the variance. Your interest is in the probability. So first of all, we need to find out the sampling distribution of this. So we know that this again would be normally distributed with mu1 minus mu2, that would be 2, and the other one would be sigma 1 square, that is, let me just write it directly. So it would be 4 by 20 plus 4 by 25. So this would come out as 0.36. So when you are interested to find the probability that this sample mean is greater than this, so here you can just simply standardize it. So here xa bar minus xb bar, so you will subtract the difference of the two means, minus 2, and you will divide it by the square root of this 0.36. Again, same you will do over here, 0 minus, so here you will have 2, and you again will be dividing by 0.36. So this over here is your z, and here you will get something around minus 3.33, which when you look at the standard normal table, it would come out approximately 0.996. So we will see all these examples and see how it can be solved using Python. So now we are done with two cases. In both the situations where the variances are known to us. Okay. So variance is known, but in first case the two variances were different, and in the second case we assume that the two variances are same.